All right, well, welcome and thank you everybody for joining us both in person and over Zoom for today's C2 Smart seminar. I am Lizzie, Research Project Manager at C2 Smart, which is a US DOT Tier 1 University Transportation Research Center. And C2 Smart leverages recent advances in big data and technology to solve today's urban mobility challenges. Today's seminar is Design Mobility as a Service Platform as an Intermediary. Our presenter is Dr. Zhang, a postdoctoral researcher at the Automatic Control Laboratory at ETH Zurich. Her current research lies in the intersection between transportation research, machine learning, and game theory. We will be recording this presentation and then uploading it to C2 Smart's YouTube channel. And we encourage everybody to ask questions today. And if you're joining us over Zoom, you can do so by pressing the Q&A button at the bottom of the window, and we'll read out your questions at the end of the presentation. And then if you're there in person, we can do it at the end as well. And with that, I will hand things over to Dr. Zhang to get us started.
Thank you for the introduction, and thanks everyone coming to this talk, both physically and virtually. So this is super fresh work. I just finished the draft paper like 1 week ago, and it's a joint work with Dr. Ray Yao. And in this work, we're trying to design a mobility as a service platform as an intermediary. So maybe not sure everyone is familiar with this concept, so I put this one slide to introduce MaaS. So based on this definition by the European MaaS Alliance, the MaaS platform should be able to integrate various transport services into a single on-demand mobility service and offer the travelers with access to the mobility through a single application and payment channel. And this concept of MaaS can create new business models for organizing and operating different transport options. And finally, it is expected to provide us an alternative to private driving, and it should be more convenient, maybe not as convenient as driving, but similarly, but more sustainable and cheaper. So why I'm interested in MaaS, it's all about my personal experience of multimodal travel. So I've been spent almost 6 years in Chicago, and one trip I often made is from my home to Chicago airport. So if you search on Google, Google gives you two options. The first one is to take the bus, which take around 1.5 hours, and it's pretty cheap. And the other one is to take Uber if you don't have a car. And normally, if there's no traffic, it's just a 30 minutes drive. But if there is traffic, normally happened in this area, the travel time is long. It can be super long and up to 2 hours. And the cost is also much higher than a bus. But what I did is usually take the Uber to a metro station and then take the metro to the airport. Although it was much longer than Uber if there's no traffic. Normally it takes 1 hour, but it's much cheaper than Uber itself. And the travel time is more reliable because there's no traffic on metro. And this is only the one-way trip from my home to O'Hare Airport. But when I come back from O'Hare, I normally do Uber pool instead of transit because the transit travel time or the schedule is not that reliable. And this will cost me sometimes up to 1.5 hours and around $40. And this is my story in Chicago. Now I moved to Zurich, which is well known for its public transit. And here's an example about how I get to IKEA to find new furniture. So normally I will take the tram to a train station and then take the train to the IKEA outside the city. What I found is more amazing about this the Swiss transit app called the SBB, and it has a special feature called Easy Ride. So basically, you only need to swipe and swipe when you start a trip and swipe back when you finish the trip, and the trip fare will be automatically calculated based on your trip origin and destination. So that is the one idea MaaS example in my mind. And that's also the main motivation of this study. So if we look at the role of MaaS in the transportation system, I really like this classification given by Professor Van der Berg recently. So based on the integration level, we can classify MaaS platform in different ways. So at the very low level integration, we have the MaaS platform that provide us multimodal trip planning. And then we may have an integrated payment where the MaaS platform performs like a broker in this multimodal travel system. And further, we can have an integrator, a MaaS integrator, which set price on this multimodal trips and takes part of the trip revenue as its own revenue. But what we are looking at today is the case with the highest integration level, where the MaaS platform play as an intermediary in the system, which buy service capacity from the service operators at a wholesale price and sell multimodal trips to traveler. So when we look into the literature on MaaS, we found so first we have a lot of empirical study. One direction is to do the survey on potential user of MaaS and ask whether they have the intention to use MaaS and given which condition they will prefer to use MaaS. And another direction is to do a small case study on certain type of integration between multiple transport services. And then the research moved to the more network design problem, where we have either a last mile mobility service or a more general integration between different transport services. But what we are talking about today is more on the platform operation side. So under this topic, there are also different tracks. So some research work on the bundle pricing and the subscription design. But what we are looking at today is more on the trip assignment and pricing problem. And I want to highlight the work by Professor Zhou, because it's his work really motivated my research on this topic. But I use one sentence here to differentiate our work with a previous study. So here in this work, we try to explicitly model a MaaS platform as an intermediary in the transport system. I will give more detail like how this works in the model. So this is the general diagram of MaaS we are considering. So as a MaaS platform, it will buy the service capacity from different operators at a wholesale price. And also, as I mentioned, it will sell multimodal trips to MaaS users only based on their trip origin and destination, regardless of the mode they take. And also we have some non-MaaS users who use the same service in the system. So they will have interactions with the MaaS users. So the framework is nice, but then we found that there were several yes?
Sorry, first question. So for the non-MaaS users, they can take individual modes, or are they also beholden to a combination?
They can also take multimodal trip like me, but then we assign certain like a planning cost on each trip. And also they need to pay the trip fare separately. for each leg of the multimodal trip. So here are some major challenge we have in this work. So first, this is a joint assignment and a pricing problem, which is rather complex than the classic assignment problem. And secondly, because we want to do this OD-based pricing, we actually have give the full flexibility to MaaS travelers to do their own routing. So this will create another layer of difficulty in the model. And thirdly, as I mentioned, we really need to deal with the interaction between MaaS travelers and the non-MaaS traveler in the system. And finally, because we use this many-to-many matching diagram, we need to establish the so-called stability condition, and we need to reduce that for the particular problem we are considering about. So to tackle this major challenge, first we adopt this many-to-many stable matching framework, which is first used by Professor Zhou, and we feel it's a nice framework because it basically decomposes the original complex problem into two subproblems. So the overall problem can be more easily solved. And secondly, because there is a routing problem for the MaaS travelers and also non-MaaS travelers, we are integrating some equilibrium constraint into the assignment problem. And thirdly, as I mentioned, because the MaaS travelers and non-MaaS travelers are interacting in the network, we are actually dealing with a network assignment problem with link interaction. And finally, to derive the more explicit stability condition, we propose a attribute-based capacity purchase scheme, which largely simplify the pricing problem and the stability condition. This is just a brief introduction on the many-to-many matching. So it's all start from the one-to-one stable matching, date back to the 1960s. So we have a group of buyers and a group of sellers. By matching with each other, they can get the different payoff. And we use the alpha ij to represent the total payoff of each match. So the matching is called the stable if no one has incentive to break the current match. That is to say, like there's no other match that bring higher payoff to both users, to both buyers and sellers compared to their current one. So this is one-to-one matching. Then people start to extend this idea to many-to-many matching. And in this case, each buyer can be matched with multiple sellers, and also each seller can be matched with multiple buyers. And the stability condition is changed accordingly. So basically, the idea is if the matching is stable, if we cannot find a matching that is better than the current ones, and and the current one is no longer the single matching, but evaluated by all the matchings for each buyer and seller. Okay, and how we translate this many-to-many matching into the MaaS system. So here is a very simple example. We only have one OD pair, and we have three types of services, the public transit, the bike sharing, and the ride hailing. And currently we have three different paths from the origin to the destination. And in this case, each operator has multiple service link, and this link will combine together to be the multimodal path. So the matching will happen on the multimodal path. On the demand side, we allocate the demand flow onto this different multimodal path. And on the supply side, different operator will support this demand flow on each link. So that's how the many-to-many matching is happen in this system. And also, like if we still use the terminology of buyer and seller, now we are dealing with each OD pair as a buyer and each operator is a seller. And the matching, again, is happen on the path. So in this case, we call a MaaS matching or assignment is stable if for all the MaaS participants, there's a no feasible MaaS path that gives a higher total payoff, but it is not used. Or the MaaS participant can deviate from the system to choose non-path travel. In this case, there need to, the stable condition says like there's no other feasible non-MaaS path that gives the higher total payoff. So I will translate these two conditions into the mathematical form later once we have the assignment result. So this is the MaaS system we are considering. We have a multimodal transport network, and to make it better for modeling, we separate the network into subnetworks. We first have a subnetwork that contains all the origin and destination, and then we have subnetwork for each type of a service operator. And further, we assume this non-MaaS travelers can also opt to solo driving. So there's a driving network at the bottom. And in this, in all this network, we have regular links that represent the real physical trip. We also need to define some access and egress link to represent the waiting time, the matching time in different type of services. And further to connecting the subnetworks, we define some dummy link from the trip origin destination to different subnetwork, and also some transfer link when the travelers need to do a mode transfer. And another slide about the setting. Here we just define different set of links and define the travel time on each type of link. So for the transit, the empty, it's quite simple. We assume everything is constant. But for the mobility on demand service, we now here we consider the ride hailing service. So the travel time on a regular link really depends on the real traffic on the road. So we implement the BRT function as a function of the total travel flow on that link. And for the access link in the mobility on demand service, we need to consider the matching process between the vacant vehicles, which is represented by this capital V, and the number of waiting passengers, which are represented by the total flow on the access link, and compute the waiting time as the access time, as the time on the access link. And further, when there is a mode transfer, we assign a constant transfer time for all type of mode transfer. Okay, and here are some assumptions we made in this work. We believe some of them can be further relaxed, but we start from the easy one. So first, we assume this service is fixed and exogenous in the way that the service capacities are fixed, the total demand are fixed, the non-MaaS trip fares are fixed. So only the MaaS platform is playing around with the demand, playing around with the MaaS demand and the MaaS pricing. And further, because we use the OD-based MaaS trip fare, the MaaS travelers can freely choose their route to minimize the total travel time, but it has to be subject to the capacity constraint. And similarly, the non-MaaS travelers can take a self-designed multimodal trip, but they are subject to some planning cost, and also subject to the non-MaaS service capacity. So this is the first part of the joint design problem, which is the MaaS assignment. So here we try to design the how much travel demand we want to capture as the MaaS traveler and assign them to the multimodal transportation network. And the overall objective is to minimize the total travel time in the system, and is subject to different type of constraint. So here, this first one is simply the demand split. We split the fixed demand between MaaS and non-MaaS. And then we have the capacity constraint for the mobility on demand service. Here we assume like there is a minimum level of service represented by the minimum vacant vehicle. And we also need to satisfy the flow conservation constraint. And this single line tells the capacity constraint of the mass transit. And the next two are the equilibrium constraint related to the routing behavior. And this is just the feasible condition for the link flow in the multimodal network. Okay, I don't miss anything here. So with this original formulation, we turn it into a bi-level program because the original problem is super hard to solve. So basically, if we assume the MaaS platform aims to maximize its profit by designing the pricing scheme, then we can get this result that at the optimal assignment, the purchased capacity equals the consumed service and consumed capacity. So using this result, we can rewrite the original assignment problem into a bi-level program. So on the upper level, the only decision variable is how much demand we want to capture as a MaaS traveler. And once this Q is determined, we move to the lower level problem to solve the routing problem for MaaS and non-MaaS traveler. And the lower level problem can be written as a variational inequality with a slightly different cost function and feasible set. So then we can prove that this optimal assignment always exists if we have this precondition on the market clearance. Also, we need to have two mild condition. The first one is the mobility on demand capacity should be sufficient, which means we always need to have some vacant vehicles roaming on the street. And second, the mass transit capacity should also be sufficient such that at least there is a feasible assignment when we assign all the demand to MaaS system. So with these two mild conditions, we can prove the existence of that bi-level program and also the optimal MaaS assignment problem. So here's the overview of how we solve this bi-level program. So as I mentioned, the lower level is formulated the VI, but still it's different from classic VI. We have an extra constraint on the mass transit capacity. So, so this brings another difficulty. So to overcome this difficulty, we design a relaxed VI problem. So we put the constraint into the cost function so that we can use the original VI solution algorithm to solve that. And further, because when solving the upper level problem, we need to have the sensitivity of the lower level problem. So we need to reformulate this VI again to make it tractable when we try to find the sensitivity. So the idea is to do this so-called operator splitting. And what we really do is to create a auxiliary variable and do the fixed point iteration on this auxiliary variable as well as the regional variable. And this fixed point iteration is shown to converge to the relaxed problem if we well design the step size. So once we have the solution to the VI problem or approximate solution to the VI problem and its sensitivity, we can use this information to compute the gradient at the upper level and do the first order method to update the mass demand the mass demand allocation. So as a summary, in each main loop, we first run a fixed number of fixed point iteration for the relaxed VI problem, and then do backward propagation to compute the sensitivity of that solution, and use these two information to evaluate the gradient information at current mass assignment, and then do the update on the multiplier for the mass transit capacity constraint, and also another penalty values for also for that capacity constraint. And this iteration will terminate when we found that the difference between consecutive iterations is below a certain threshold, both in terms of the mass demand and the realized equilibrium flow. So now we have the optimal assignment of the mass system. We need to use that result to derive the stability condition in this case. And here are some key elements we need to know beforehand. So as I introduced in the beginning, we have to define the payoff for both the mass, non-mass travelers and for the different operator with respect to a path in the system. And here we translate the stability condition into two inequality constraints. So the first one, as I said, we cannot find a feasible mass path that give us a higher total payoff for each OD pair in the system. So that gives us the S1, this condition. And the other condition prevent mass participants to deviate from the mass system. So that is to say we cannot find a feasible non-mass path that also that gives us a higher total payoff. But then we need to further specify what are the payoffs of travelers and operators. So here we need to define the utility of each trip between each OD pair, and also what is the mass, the pricing on both the supply and demand side. And here we use PD and PS to represent this mass fare. And for travelers, for the mass travelers, the payoff is equal to the utility minus the total travel time minus the OD base pricing. And for non-mass traveler, it is the utility minus also the total travel time and the trip fare on different segment of the trip. For the operator, the payoff is simply the total revenue they can obtain from each pass per unit demand flow. So then we try to simplify this stability condition. What we first do is to show that at the optimal assignment, we can replace the generalized cost with this OD-based cost, and we can show that for all the active paths between each OD pair, this generalized cost is the same. And then using this property, we can further reduce the stability condition. But here there's a trick we play with the supply side. So instead of designing the capacity price for each link, we say we only determine one unit price and use this unit price times a exogenous attribute to determine the capacity price on each link. So using this specialized pricing scheme, we can reduce the stability condition into a very simple one, because everything in this final inequality constraint is directly available from the optimal assignment result. And further, if we have another some special property related to the non-MaaS generalized cost and the trip utility, we can further derive a simpler version of the stability condition. So that's why we include this corollary as a sufficient stability condition. So once we have this stability condition, we can turn the original formulation for the MaaS pricing problem into a reduced one. And here our objective is to maximize the platform profit under the constraint that the MaaS travelers have non-negative payoff and the operators have a non-negative profit and the stability condition. So this original problem can then be reduced to a much simpler linear program where we have everything readily, and this linear program can be solved easily by any type of solver. So we further show some properties on this stable pricing and also stable assignment. So we first show that this stable outcome always exists, and there's always a finite optimal pricing. And with another mild condition related to intermediate term we derived from the assignment problem, we can even show that this optimal pricing is unique. Okay, I'm done with the modeling. So I'll use several slides to introduce our numerical experiment. This is still pretty preliminary and hypothetical. So I wish to extend it to more real life case later. So here we use the Sioux Falls network. We artificially add some metro and bus line to change it into a multi-modal network. And we say that this exogenous link attribute is, we set them to be the non-MaaS, the trip fare. So it turns out like when we solve this PS, it's actually the wholesale discount for the capacity purchase. And further, we introduce another exogenous parameter eta to represent the revenue split between the mobility on demand service and the mass transit service. And maybe another important part, we set the trip utility as the general, the equilibrium cost of this system without a MaaS. So that means if we finally get the non-negative non-negative payoff, that means the MaaS is bring some benefit to the system. So here's the preliminary result for the assignment. So without MaaS, we found like around 30% people will choose driving, but this percentage reduced to 16% when we add MaaS platform into the system. And the MaaS platform is able to capture 60% of the demand. And we're also interested in how many multimodal trips are made by passengers. So we compute the mode transfer per trip. So as expected, once we introduce MaaS platform, this mode transfer per trip increase a lot, and most of them happened in the MaaS trip. And this table tells more story about the supply side. So we compare the capacity utilization in the scenario without the MaaS and with MaaS. So we see a increase in the utilization of both mass transit and mobility on demand service, where the increase is more significant for mass transit. And we also compute the social cost in terms of the travel time and the general social cost. And MaaS is able to bring it down by 10%, around 10%, which is quite promising. Then we move to the pricing result and compare the traveler's cost and basically the welfare of different stakeholders in the system. And here because we introduced this price factor, and a different price factor, we can get different result. So we focus on 3 different cases. When the travelers are optimized, the platform's profit is optimized and operators' revenue is optimized. But we introduce a constraint on non-negative profit for the MaaS platform. So in these 2 cases, the MaaS platform has 0 profit. So when the travelers are optimized, we can observe around 5% decrease in their average travel cost, including the trip fare. And when the MaaS platform is optimized, this increase reduced, but still quite close to the similar level. And what is more interesting is the revenue of mass transit, because we observe the MaaS platform brings the most benefit to this part of this type of stakeholder. And when they are optimized, they can gain a 50% increase in total revenue. Oh, I forgot to mention this, but it's okay. And further, we compare the performance with and without MaaS platform and see how it brings to each individual traveler. So here we we separate the MaaS traveler and the non-MaaS traveler. So for the MaaS traveler, because we have a non-negative payoff constraint, all of them are benefit from the MaaS platform. So they have a non-negative cost saving. But for non-MaaS travelers, some of them are actually worse off when we introduce MaaS platform. Another interesting finding is that we actually found some of the MaaS travelers are compensated by the platform because it will bring the platform a higher efficiency. But this amount of travelers are super small, and also the compensation is relatively small compared to the positive fare. And we also compare the MaaS travelers from the non-MaaS traveler in the optimal assignment result, and find that some MaaS travelers are actually have a worse service compared to non-MaaS traveler. but why they're not deviating from the system. So if we look into the travel cost, the traveler's cost, the operation revenue, and the total payoff corresponding to each trip, we found that this matching is still stable because it still gives a higher payoff. So even though the travelers worse off, they cannot find operator that support their non-MaaS trip. So they have to stay in the current matching. Okay. It's pretty fast. Okay. So as a conclusion in this work, we try to model the MaaS platform as an intermediary in the multimodal transportation system. And specifically, we try to have the MaaS platform to buy service capacity from the operator at a wholesale price and sell multimodal trip to travelers only based on their origin and destination. So in this case, under this setting, we are actually guarantee certain revenue for the mass transit operator. So that's also why in the numerical experiment, this part of a stakeholder gets the most benefit. And by designing this OD-based pricing, we hopefully remove the boundary between transport modes. And we believe this is the real idea of MaaS in general, provide a seamless trip journey to traveler. And to solve this problem, we adopt this many-to-many stable matching framework. And for each sub-problem, we do certain simplification and derive some analytical result to make them solvable. For the assignment problem, we first turn it into a bi-level program and then introduce some relaxed formulation and develop this sensitivity-based solution algorithm to solve that assignment problem. For the pricing problem, we first simplify the stability condition and prove the existence of a stable outcome under some mild conditions. And also we find some condition where we can find a unique optimal pricing. For the experiment, as I mentioned, it's still very preliminary. It's based on a extended Sioux Falls network, but we are able to show the potential of MaaS in reducing driving, encouraging more multimodal travel, and increase the transit utilization, and overall improving the system efficiency. We show that if the pricing scheme is well designed, we can ensure the profitability of MaaS platform. And also we observe the largest increase in the mass transit revenue. But we also find that the introducing MaaS platform in the system may induce some negative impact on MaaS traveler. So this is something we need to really care about. So with that, I'll finish my talk. Thanks for attending and listening, and then open to questions.
Thank you so much. If you are on Zoom and you have a question, feel free to add it to the Q&A and we can read it out. Otherwise, we don't have any at the moment. So if there are any questions in real life, you can take those first.
Yes.
Yeah, so it's a quick question. Really quick one. I was wondering about the transfer costs, at least for the Sioux Falls examples. How sensitive are the results to?
We haven't done sensitivity analysis on that, but that's part of the plan in the next step. So far, the transfer cost, you mean the transfer time or the extra planning cost?
So generally, the perceived cost of a transfer is higher than actual time. Access.
Yeah. I would say, so currently in the model, there are two things. There's a one transfer time, which is the same for both MaaS and non-MaaS traveler. And that one is set to be pretty small, I would say, at this moment. And the other one is the extra planning cost for non-MaaS traveler. That one is slightly larger than the transfer time. But you're right, we need to do sensitivity analysis on that to see how sensitive the result is with respect to these two terms. Yes.
So I just have a question regarding the mechanisms through which the increase of efficiency occurs on the MaaS platform. So if I understood correctly, for the MOD, the sort of access time and waiting time depends on the number of users. But for the public transit, is that the waiting time also dependent on number of users?
Currently not. It's set to be constant. So it's similar to the headway of a train, where you can assume it's relatively stable compared to the MOD service.
So it seems that the increase in efficiency comes from the MOD.
Increasing efficiency in terms of what?
Because I little understood it. You mentioned that the service becomes more efficient.
Yeah, yeah.
And that even some users are subsidized, right? In a sense, because they make the service better. So I'm wondering, where does that come from? And it seems it's from the MOD.
Yeah, it's not only MOD, but also the general traffic on road.
I see. Right.
Yeah.
So they're sort of subsidized for giving that. Okay.
Yeah. Yes.
In the pricing experiment part, I was surprised that the MS the platform the MaaS platform doesn't get profit, doesn't get revenue under the traveler's optimal scenario and the operator scenario. So is that implying that in your word the MaaS optimal strategy is the most possible, the most possible
Sorry, I didn't get the last part of your question. You mentioned like in the result, we have a 3 scenario.
Yes.
2 of them lead to 0 profit.
Yeah,
And
so,
yeah, what is your question?
I mean, in your word, no next company would like to operate at 0 value. Right?
0, you say like if we are the MaaS platform
Yeah.
and we want to what?
I guess the question, I don't know if I understood correctly, but I guess the question is, your result kind of showing that there's 0 profit for MaaS, for a company using the type of like MaaS approach. And might not be that practically lower because none of these companies would love to see 0 profit.
Yes. So that result really depends on the price factor, which can be tuned by the MaaS platform. So it's not given by other entity. So if this MaaS platform is profit oriented, it can set the value such that its own profit is maximized. But if this platform is supported by government, it's okay to operate at no profit, then we can change that the price factor to benefit other stakeholder in the system.
Question, so there's
We can also discuss offline.
I mean, I guess as I'm thinking about it, like practically there is that sense that purchasing capacity, right, for the MaaS operator is inherently dynamic. Right? I'm thinking, if I allocate this much capacity now, what happens a few periods from now? So is there any thoughts on how you might incorporate that here?
I mean, the turn this static model into a dynamic one. Well, that's the good question. I don't have answer for now because solving the static model is already quite complex. But it's good to, I mean, like if you really want to tackle the practical problem, the dynamic model is for sure a good direction. Like how to model the evolution that people adopt this MaaS platform. But that's a wonderful future direction.
Great, and we don't have any questions on Zoom, so I think with that, thank you everybody for joining and for Dr. Zhang, Dr. Zhang for presenting at today's seminar. A recording will be made available on the C2 Smart Center's YouTube channel and website. And again, this webinar was brought to you by C2 Smart and the USDOT's University Transportation Center program. So thank you everybody and have a great rest of your day.
Thank you. Thank you.